Okay, gang, here we go. This is topic 2, graphing exponential functions, and in particular using graph transformations. Graph transformations. Now, graph transformations, this is nothing new. We've actually seen these same exact transformations back in section 1.7, so I recommend going back to there to look at those. We also talked about transformations, I believe, in the chapter where we had the library of functions. Beautiful chapter. Here we're applying them to exponential functions, which we were introduced to in the last video. And when we introduce exponential functions, we use the placeholder a as the base, right? Little a. And because of that, when we did transformations before, we used little a for the transformations. But since we already have it down there, we had to use something else. So we're using capital A for the transformation. And then following suit, we're just making all the transformations capital letters. So this first capital letter A, this one is responsible for stretching vertically, just like it was back when we introduced general function transformations. So that's a stretch. When the absolute value of A is bigger than 1, then it's a stretch up and down. And when the absolute value of A is less than 1, then it's a shrink. It shrinks your function. What I mean by absolute value less than 1, so things like half or negative a half, third or negative a third, or any fraction or decimal. And if it's positive or negative, that's a shrink. And if you have a whole number that's positive or negative bigger than 1, then it's going to be in a stretch. All right, what about number 2? So the second transformation is a horizontal stretching. But remember, when we do horizontal stretching, it's kind of a little bit counterintuitive. It's by 1 over b. So if b is bigger than 1, absolute value b is bigger than 1, that ends up being a shrink. And what do you shrink by? You shrink by 1 over b. Now, on the other hand, if you have b like something like a half or something smaller than 1, then that ends up being a stretch. Why do you get a stretch horizontally? Well, if you think about it, if I have a number that's a fraction before I multiply by x, so let's say it's like a half an x, then it takes x to be twice as big to reach the same original position, right? So because of that, you end up stretching your overall function. And you stretch it by 1 over b again. So that 1 over b kind of tells you what's going to happen, right? If it's a half, you take 1 over half, you end up stretching by 2. So it's always kind of backwards with the horizontal stretches. Okay, now for reflections over the x-axis, if a is negative, you get a reflection over the x-axis. That's a reflection up and down, right? This way, up and down. And then if b is negative, then that's a reflection over the y-axis. So that's a reflection left and right. Those kind of coincide with the stretchings, right? Did I say stretching? I meant reflection. So the b being negative coincides with a horizontal kind of change, right? So b being negative makes a reflection over the y-axis. That's a horizontal reflection. Okay, lastly, you have the translations. These are the easiest, I think, most intuitive parts. Actually, D is the most intuitive. Vertical translation by D, super intuitive, because you're just adding D to go up and subtracting the number to go down, right? And then here we have the horizontal translation for C. That's if C is positive. When I say C is positive, it means x minus a positive number. So like x minus 2 would be a translation to the right. X plus 2 is like x minus negative 2. That would be translation to the left. So x plus something is going to move you to the left. All right, let's try the questions 3 to 7. And you get a feel for what I'm talking about here. Let me copy and paste these again. Okay, let's make this a little bigger. Okay, so start one at a time with, let's do number 3 first. Okay, number 3, looking at it, it's actually a very simple one. It's just a translation down, right? So let me start by graphing the original function. This is 2 to the x, something we've seen before already. 2 to the 0 is 1, so you typically always get that if I look at the original f of x equals 2 to the x function. It should look something like this, right? At 2, you'd be 2 to the, at 1, it's 2 to the second, which is at 2. And at negative 1, you're at 1/2. Okay, so this is f of x is equal to regular old 2 to the x, right? Now, if I subtract 3 to that, then I'm moving this whole thing down by 3, right? So down 1, 2, 3. So that puts me here at -2. And otherwise, everything else kind of, the shape is still maintained, right? So originally, if we look at my positions, I went from the starting position, I went 1 to the right and 1 up. So that same thing's going to happen here. 1 to the right, 1 up. That puts me right there. And from here, I went 1 to the left, down a half. So I do that same kind of translation. Down left 1 and down a half. So that puts me right there at -2.5, yeah? So there's a rough sketch of that function based on the translations. Okay, so that's number 3. I'm sorry. I forgot to answer the questions here. It says to identify domain, range, horizontal asymptote. So domain first, -infinity to +infinity. Nothing has changed. The range, okay, the range is from how far down are we going? This new, so the original asymptote was over here, right, at 0, but that got moved 3 down. So here we are at -3. And so the lowest you can go is -3, and you can go all the way up to +infinity. And then what about the horizontal asymptote? Horizontal asymptote always coincides with that end of the range. And that would just be HA for short, y equal to -3. Okay, also be on the lookout for a pattern here. Okay, be on the lookout for a pattern. I won't reveal it yet for horizontal asymptote, but I think it's going to be pretty obvious how we can get that horizontal asymptote. So just think about it for a minute. Try to figure out where you could get that -3 just looking at your function. Okay, that's number 3. Let's go on to number 4. Okay, so number 4, I have 3 to the negative x plus 1. So 2 things happening. I got this negative, which would be like the b being a -1, right? And then you have this +1, which is like the d part being a +1 at the end. So let me start with the original 3 to the x, the regular old 3 to the x. So here's your x coordinate, y coordinate. So 3 to the 0, that would still be at 1. So I still get the 0.01. 3 to the first power would be 3. So you notice you go 1 to the right and 2 up, yeah? And then 3 squared would be 9. Actually, I'm not going to include that point because make it simple as possible. 3 to the -1 would be 1/3. So about here somewhere. This would be the original function, right? This would be f of x equal to 3 to the x, original exponential function. Now from here, okay, if you follow the conventional method, you'd apply this b transformation first, which b is negative. That means it's a reflection over the y-axis, yeah? Because this is, the b represents a horizontal change, so it's a reflection this direction. So I'm going to graph both in the same plane here. Reflection here would mean I go left 1 and up 3 instead, and then right 1 and down to 1/3. So did I say up 3? I meant up to 3. Yeah, so it's actually up by 2 points. Okay, and then it should look something like this. Right? Okay, and then lastly, apply this +1. So then that moves this whole thing up by 1. Something like this. Okay, now let me redraw these points here. This one would be at, so notice from my new starting position, right, at 0, 2. If I go left, I should go up by 2 points. Why? How do I get 2? Well, remember earlier, as the same relative position, right? Left by 1, up by 2. And then from here, right by 1, down by 2/3 to get to a positive 1/3. So this point should be, actually it looks kind of a little off, but this should be at 1/3. That would be 1 1/3. This should be 1 1/3 here. Yeah. Okay, I'm going to erase this original graph so you can see it more clearly. And then now, what about the horizontal asymptote here? Horizontal asymptote should be at wherever that line is headed, which is at +1. Yeah. Let's answer the 3 questions now. So the domain first, -infinity to +infinity. The range is from +1 and up forever. So 1 to infinity. And then horizontal asymptote is at, y equal to positive 1. Okay, are you seeing that pattern now, that positive 1, yeah? Let me also show you guys how, the original way I would have graphed this if I was to just shift the center point first. So another option is to, from your original graph of 3 to the x power, which is something like this. Right here, actually, yeah. So from there, the center point is right here, and then that means you have your horizontal asymptote right here, right? Well, if I shift to this center point here up by 1, so that means that my graph, the way my graph changes is this guy is now up by 1. Here's my new horizontal asymptote. Right, my new horizontal asymptote has shifted now. And then now I'm going to do the reflection. And by doing the reflection, I end up with this picture. Oops. This picture, something like this. So originally, I was at 0, 1, now I'm at 0, 2. And then negative 1. And what was that, 4? So this should be a third, 1 and a third. 1, 2, 3, 4, yeah. It's kind of ended with the same thing, right? All right, so that would be shifting, kind of thinking of the center from 0, 0. Again, that's kind of more the unconventional way. More conventional way is just to do it in order of alphabetical order by transformation. Okay, number 5. What's happening here? This is basically 2 to the x, right? Plus you got some horizontal shift and a vertical shift. This is an easy one. I know maybe it doesn't look the easiest off the bat, but actually it's easy because there's no stretchings. Stretchings is what makes things a little more complicated, but there's none here. It's just a regular move to the left and move down. So we do it in pretty much one. Let's just skip the original because we already know what 2 to the x looks like, right? Let's jump straight to the chase here. Negative 5 and this is x plus 3. That means to move to the left, right? So normally you have this starting position 0, 1, right? That starting position is going to move to the left by 3. 1, 2, 3. So now I'm over here, and then down by 5. 1, 2, 3, 4, 5. Now I'm at negative 4 here. So down over here. Okay, so that's my new starting position. And otherwise, the shape should be the same. What's the original shape of 2 to the x? Well, if I go to the right 1, I'm going to go up 1. If I go to right 2, I'm going up by 3. Yeah. Okay, maybe it would have been good for me to actually draw that so you guys could see the original shape. This is the original shape of the graph. Oops. Here I am down at a half below, 1/2 below. So here's the horizontal asymptote, right? Down at negative 5. Okay, that is not straight. Try that again. Okay, that's more straight, but missed the line. There you go. Okay, so the original shape, we're here to the right at 2, right? And then 2 more, 2 squared would be 4. So here that's 1, 2, 3 up from the original starting position, yeah? And then to the left, you're down at a half. So this is the same shape here as over here. Okay. Let's connect the dots here. So there you go. That's in purple is our final result here of 2 to the x plus 3 minus 5. Domain is negative infinity to infinity, like it almost always is here for exponential functions. Range is going from negative 5 and upwards, and the horizontal asymptote is at y equal to -5. That's a horizontal line. Horizontal line, remember, has a form y equal to a number because the height is never changing. Okay, so, oh yeah, -5. See that pattern? Okay, I'm just going to spell it out for you now. At this point, hopefully you've seen the pattern. Let me show it to you. So -3, if you remember, that was the original horizontal asymptote for number 3. +1, that was the horizontal asymptote. And the question we did just now, -5, right? So the horizontal asymptote is given away by whatever that d value is. You just set y equal to that, and boom, that's where it ends up. Which is consistent with moving our center point, right? If you move your center point from, if you think about the center point as being 0, 0, not really center point, but if you think of your origin, how your origin moves, well, it's going to move up or down according to that d value, right? And then that is exactly where the horizontal asymptote lies, because the original horizontal asymptote is at y equal to 0 if you don't do anything to the graph, right? If you don't do anything to the exponential function, it's going to be at y equal to 0. But then if you translate it, the thing going to translate. Okay, so here we go. Number 6, f of x equals... Okay, so one thing about number 6, it's 1 minus 3 to the x, which is a weird way to write an exponential function. The more natural way is to write it as -3 to the x plus 1. And then we can see that, okay, this is the meat of the function. And then you're just adding 1, yeah? Okay, here's another case. So, you know, it's easy to mess this one up, because if you start from your normal position of 0, 1, right? And you think, okay, I'm just going to shift this thing up, and my new starting position is going to be 1 up higher than that. Well, this is going to end up being actually wrong. This is going to be wrong, because this point is not on the graph. And the reason why it went wrong is because of the order. One way to think about transformations is you can just apply them in the proper order of operations. So like, what happens first? This is a minus being multiplied by the original function. So that should be the first transformation to do, right? So you do it in that order. Or, or just doing it in alphabetical order, right? So this point 0, 2 has nothing to do with the graph. It's not on there. Let me just redraw that thing. Okay, so what should you do? Well, what you should do is do this apply this negative first. That's a -1 for the a, right? Which means you're reflecting over here, over the x-axis. Okay, normally 3 to the x should look something like this, right? You pass to this point, you go up to that. But then if you're reflecting over the x-axis, this point where it's at 0, 1, it should look now like this, right? So it should be over here, since I'm reflecting over this axis here. And then instead of going up this way, it's going to go down this way, right? Okay, now if you apply this +1, that's going to shift this whole picture up by 1. So this is going to go up right here. And so that's where you're going to end up. Okay, and then that makes my horizontal asymptote right over here. Yeah, y equal to 1. And then this gives you now the correct result. This is the general shape of it, yeah? And if you're looking for exact let me do this. Okay, if you're looking for some exact points, well, I have one of them already. That one of them being, not that point, this point at 0, 0 actually, yeah. And then I also I can get the other ones pretty easily. If I go to the right one, I'm going to go down to a third. Why a third? Because 3 to the what is it? 1 over. Oh no, I'm sorry. It's not a third. It's this is a change of a third. So for the left one, this guy is gonna be, the position is like 1/3 over here, so that's like actually at 2/3. Yeah, 2/3. So -1 at comma 2/3 is the point. That's a little off. Should be like that. Sorry guys, my lines are kind of inaccurate here. Let's try that again. There, here, and then what about to the right? So to the right, if I cubed 3, it's gonna get me, I'm not cube, I'm sorry, I'm not cube. If I just take 3 to the 1 power, it's 3, right? But it should be negative, so it's gonna be negative 3. 1, 2, 3, and then shift it up, so it actually ends up at 2, negative 2. It's like this. But more importantly, I guess, the shape, right? The shape. If you think about the original shape of 3 to the x, I start at 1, 0, 1, and then it goes up to 1, comma 3. You're moving to the right one and then up 2. So here I'm going to move to the right one and then down 2 because it's a negative 3 instead. Okay, so there's the graph. And then let's do the answer the questions. The domain, negative infinity to positive infinity. Range is up until it hits 1 as the highest, right? So it's kind of opposite. It goes from negative infinity to positive 1. And what's the horizontal asymptote? That's going to be y equals to 1. There. Okay, real quick, how would I graph this if I wanted to just think about the origin shifting? I guess I gotta redo this. Oh no, there we go. So the origin is right here, right? 0, 0. And the origin is part of the horizontal asymptote. So if I just think of shifting that horizontal asymptote by the transformation of +1, there's no horizontal transformations here. Then my new starting point 0, 0, my new origin position is now right here, right here. Okay, and then I think, okay, I'm doing no negative or reflection from here. So from this new starting position, normally I go 1 up to start, right? But this is negative, so I'm going to reflect. That's going to put me down here. And then continue the rest of the graph. You're going to end up with that same picture we had. Okay, but again, just follow the conventional methods, probably safer for you as you're doing these. So we can do the way we did it first. Just apply the transformations in the alphabetical order. Okay, last one. Okay, interesting question here. I've got 0.5 times 2 to the x minus 4. Now, there's an obvious relationship I see between 0.5 and 2. 0.5 is just a half, or 1 over 2, right? So to me, I feel like the easier way is to do a little algebraic manipulation here. But I don't know if you guys will think about it the same as me. I don't know if you think that's easier. I think you might think it's easier just to routinely apply the transformations. So let's do that, and then I'll show you alternative way after as a bonus. Okay. So routinely applied transformations. Here I've got a equal to 0.5, right, or 1/2, and here I've got a c equal to a 4. Those are the two transformations I see. Here, let me break that down to what I was talking about. So if you think about it like this, the original form, fx equals to a to the x minus c, bx minus c plus d, right? Here, this a is at 0.5, and this c is at 4. So the two transformations happening, b and d are just, d is nothing, d is gone, d is 0, and b is just b1. So then in this case, those are the only two transformations. 4 to the right, and scale by 0.5. So the conventional way is just do that scale first, and then apply the movement after. So original function is 2 to the x, right? 2 to the x has a point at 0, 1. Now I'm going to scale this by 0.5. So scaling it by 0.5, that's going to pull me down to, instead of 0, 1, 0.5. And then normally I go to the, normally the point is, where is it? Okay, normally the point is at 1, 2, but because I'm scaling, it's going to be 1, 1. And then 2, 4 would be my normal point, but I'm going to scale that down to 2, 2, right? Half of 4. Okay, and then from there, let's actually do one more point. So normally I go one more. This would be 2. This would be 3 comma 8, but because I'm halving it, it'd be 3 comma 4. 1, 2, 3, 4, like this. Okay, and so I get this picture. This is just the scaling, the stretching, or actually compressing that's happening so far. Yeah, and then from there I move it to the right by 4. So you take this whole picture and just move it to the right by 4. Oh, let me do this. Let me redraw my points. 1, 2, 3, 4. Right here, 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 and there. I'm just gonna grab this thing and hopefully I drew it accurately so that I can just shift it, match it up. There you go. Okay, so there's my new picture. Here's those little points. This one is not longer a point. Okay. And just looking at the thing, we can see, okay, it's approaching the same original horizontal asymptote at y equal to 0. We can answer all our questions already. Domain is negative infinity to positive infinity. The range is going to be from 0 to infinity. And then the horizontal asymptote is going to be at y equal to 0. Yeah, okay, so we answered all the questions, got the graph of the thing. Good, we're all set. Now, what I do want you to notice is where this point is right here. Right here. That's at 1, 2, 3, 4, 5, right? At 5, you're exactly at 1, which is kind of curious, right? That looks like sort of the normal starting point where you'd have 0, 1, yeah? And that's not a coincidence. Check this out. This is the other method I was talking about, how to graph this thing. Just requires a little bit of algebraic manipulation at the front. So if I think about f of x equal to 0.5 times that, 0.5 is really a half, right? 1 over 2 times 2 to the x minus 4. Well, what is 1 over 2? 1 over 2 is actually 2 to the negative 1. So I've got 2 to the negative 1 times 2 to the x minus 4. And we haven't talked about this. We'll talk about this in the next video, actually. But rules of exponents say when you're multiplying two things together that have the same base of the exponent, then you just add their exponents together to get the final result. It's like when you say 2 to the 3rd times 2 to the 4th. What is that? That's 2 to the 3 plus 4, or 2 to the 7th, right? So same thing is happening here. 2 to the negative 1 times 2 to the x minus 4. This is 2 to the negative 1 plus x minus 4, which is 2 to the x minus 5. And what is this graphically? That's just a shift 5 to the right. Well, check this out. That's exactly what we have here, right? The normal original function would be at 0, 1, but that shift 1, 2, 3, 4, 5. So that coincides with the new graph. Same thing, you'd have 1, comma 2 as a point, right? Shift that 1, 2, 3, 4, 5, and boom, and I know that's why. So alternative way to graph the same thing. Both are correct. Both methods would be correct. Okay, guys, that's it. Graphing exponential functions.